Well, the first part that really bothers me is the fact that they just minimize and slam the scientific method. They accuse it of being linear. They oversimplify it to mischaracterize it. And it's almost as if the authors want to convince judges that it's okay to use inaccurate, untested, poorly predictive models that should be accepted over rigorous testing.
This is Climate Debrief, brought to you by the CO₂ Coalition. I'm Angela Wheeler. In a moment, we'll be having a conversation with a highly accomplished scientist and educator, Dr. Sharon Camp. Dr. Camp serves as a senior education advisor for the CO₂ Coalition and is the creative force behind the CO₂ Learning Center's engaging lesson plans. With a bachelor's and master's degree in geology from the University of Georgia and a PhD in analytical chemistry from Georgia Tech, she brings rigorous scientific expertise. Her career spans industry, the U.S. Environmental Protection Agency, and 2 decades in the classroom. For 15 years, she taught high school advanced placement environmental science, and she spent 9 years as a national grader for the AP Environmental Science exam. Now retired from the classroom, she's channeling that passion and expertise into helping educators and students alike explore the vital role of carbon dioxide in our world. As with other CO₂ Coalition members and staff, scientific integrity is of utmost importance to Dr. Camp. On March 3, 2026, she published a must-read piece for the CO₂ Coalition titled Muddling the Judiciary's Understanding of Science. In it, she praises the removal of a biased climate change chapter from the Federal Judicial Center's reference manual on scientific evidence. But she warns that a remaining chapter called How Science Works is still poisoning the well with bad science. Dr. Camp, it's an honor to have you on Climate Debrief.
Thank you so much, Angela. It's an honor to be here.
Dr. Camp, could you walk our audience through why you see this How Science Works chapter as such a serious concern for the judiciary, even after the climate chapter was removed? What makes it so troubling in your view?
So you go through How Science Works, and you notice that the very first thing that they do is try to define some of the basic scientific words that are used. For example, hypothesis, theory. They don't even talk law, scientific law, and then on top of all of that, they add modeling, which immediately indicates that they want modeling to be considered a form of scientific evidence, which it is not. So let's take a look at those kind of really briefly. Their definition of hypothesis is a potential explanation for a natural phenomenon, regardless of the extent to which the explanation has been investigated or the amount of evidence supporting or refuting it. This sounds like a vernacular definition of hypothesis. What you and I would use as a general public, a lot of people use the word theory instead of hypothesis, but basically it's just, I think this is what happened. Which is not a scientific hypothesis, which is, one of my very first problems with this. The definition of hypothesis is it's a proposed explanation for a specific phenomenon that can be tested through rigorous experimentation and observation. So it's a tentative relationship that predicts a relationship between the different variables in the process. And it has to be written so that it's testable. In other words, I have to be able to figure out whether or not this hypothesis is true. So you have different types of hypotheses, which I don't really need to go into here, but it has to be testable. It's not some nebulous idea about something. And it is supposed to be examined carefully. So their definition leaves out the most important concepts of testing, observation, and experimentation. Okay? Let's take a look at their definition of theory. They call it a concise, coherent, and predictive explanation for a broad range of natural phenomena that integrates and makes sense of many hypotheses. Okay, again, we're missing out on a whole lot of really important words here. So a better definition is well-substantiated explanation of a natural phenomenon that is based on a large body of evidence and has been rigorously tested through the scientific method. Okay? So they leave out evidence, they leave out rigorously testing, and they also leave out the scientific method. Then they include model as a scientific term, which I think is very interesting, which also kind of gives you an insight into what their purpose is and where they're going with this whole how science works section. They say that it is a mathematical representation of hypothesized mechanisms and interactions within a system that can be used to investigate the impact of parameter changes on predicted system outcomes. So let's go back and look at their word hypothesis again, okay? Their definition of the word hypothesis is a potential explanation. But they're using that to defend a model as being some type of scientific evidence, mathematical representation. So if you're going to use something like a mathematical formula, for example, those have been rigorously tested through numerous experimentations over decades. Those are usually called laws. There's a bunch of different examples that I could give you. And that would be a mathematical model which is used as a tool to be able to predict an outcome. So examples would be gas laws. You know, what happens to the volume when I squeeze a gas? What happens to the volume of a gas when I heat it up? Those are predictions, and the mathematical models will allow you to define those terms with numbers, okay? But what they're saying is that a model is made of hypothesized mechanisms which they've already identified as something that may or may not be supported. So how is a model any kind of tool for anything using their definition? Then last, let's go to scientific law. Their definition of a scientific law is an often mathematical statement of the relationship among observable phenomena. Okay? A better definition is a law describes or predicts a range of natural phenomena based on repeated experiments or observations. It summarizes the results of these observations, basically. Again, it leaves out predictive nature of a law. It leaves out the repeated experiments and observations. And at no point in time in any of these definitions does it say anything about falsification. In other words, all of these things can be disproved. All of them can be falsified. And I had used this example, I think, in the article where Buzz Aldrin was on the moon for the first time ever. And they're in an environment that is a vacuum, i.e. there's no gaseous atmosphere. So he wanted to do an experiment where you drop a hammer and a feather, because Newton's law says that gravity is going to act on them equally, regardless of their mass. But on Earth, we have air. That gets in the way. So the hammer can slice through the air, no problem. The feather gets caught and then slowly falls down. He wanted to try this on the moon to demonstrate this law. But he also understood that it had never been performed in a vacuum before, right? So he goes behind the, and I heard this story when I was visiting Huntsville, Alabama, at their museum that they have there for NASA. He goes behind the camera so that nobody can see him, and he drops the hammer and the feather together to make sure that they actually fall at the same time. Because the last thing he wanted to do was like disprove this law that had been accepted forever in front of an international audience and have absolutely no explanation as to why it didn't work. So he tested it off camera first. So Buzz understood that even laws can be disproved, but nowhere in any of these definitions does it say anything about that. So the problem that I have is their minimization of the scientific method and their redefinition, a kind of a loosey-goosey way of defining science terms and including the word model as some kind of a valid, always some kind of a valid explanation. So there are really two different kinds of models. Let me clarify that too. There are models that are used to help people understand phenomena that they cannot see. For example, the model of an atom. So every little kid in elementary school is taught about the nucleus and the electrons and so on and so forth. This is a model. Actual atoms don't look like that at all, but it helps us to understand their structure. Then there are predictive models, which is what they're talking about specifically here. And a predictive model is something where you put data into it and you get data out of it. So the best example I can give you right now of a predictive model is the weather models that they use to predict the weather. And so everybody's experience has been, okay, so the models are getting a little better, but still you really can't trust the forecast more than 3 days out. Sometimes I can't even get it right for the next hour, right? This is a predictive model. So they're only as good as the information that you put into them, and the information you put into them is only as good as your understanding of the system. So if you're looking at a system that's insanely complicated, like weather, it makes it very difficult because you really don't understand the system, and you can't introduce chaos, which occurs but is not predictable. So this is the big problem that I have with this.
Could you walk us through what the traditional scientific method actually requires and why the manual's version falls so short? I think our audience would really benefit from hearing the contrast laid out so clearly.
So the traditional scientific method follows the following steps. You start by asking a question. I see something that happened and I don't understand it. Why did this happen? That would be a great example. Then you go back and you gather background information. Go online, see if anybody's noticed this before, if somebody already has an explanation for it. If they do, then you don't need to go any further. And if they don't, then this is a possible new area of study. So then you come up with a good guess about what the mechanism might be. But the key concept is testable here. You've got to be able to support or disprove, refute your hypothesis. So it has to be something that you can test on a short-term basis and say, well, hey, this seemed to work. Maybe this is the reason. Let's continue forward with this area of investigation. Or, nope, this clearly has nothing to do with it at all. Let's look at some other factor. So that's making your hypothesis. Then you perform experiments or make observations. So the example that they like to give to break down the scientific method is that it only occurs if you can experiment in a laboratory, which is, if any real scientist knows, that truly is not the case. There are so many disciplines where you can't not do experiments in the lab. I'm going to stick with my favorite physical science, which is geology. There's measurements that you can make in a lab, but you can't really do experimentations necessarily on every question that you might have. So I've got this mountain over here in the background. How did it form? Where did it come from? And then I can come up with a hypothesis. Well, clearly I can't do an experiment to figure out where this mountain came from, but what can I do? I can climb the mountain. I can make observations. I can collect rock samples. I can take them back to the laboratory. And there are all kinds of tests that I can run on them to determine their composition, their age, etc., etc. All of that is still part of the scientific method. So they try to oversimplify the scientific method in an effort to discredit it. Then you've got analyze your data from your experiment. So now I've got all this information. How am I going to make sense out of it? And interestingly enough, when I was teaching AP, the two parts that they had the hardest time with was designing an experiment that would actually test their hypothesis, which is a whole lot easier than it actually, a whole lot harder than it actually sounds. And then once they get their data, what are they going to do with it? They've got to draw conclusions from the observations and the data that they collected. And surprisingly enough, that was very challenging for them. So when I graded their lab reports, I graded them. One of the big parts of the grade was, did you interpret your data correctly? Is there a relationship between the independent variable and the dependent variable, or is there no information? Or do you have bad data and you can't figure it out? You've got to be able to tell me that in the analysis of your data. But kids have a hard time with that. But it's the critical part, because why are you collecting all the data? You got to make sense out of it, right? And then from that, you draw your conclusions. Yes, there was a relationship. No, there wasn't a relationship. Yes, there was, but it wasn't clear. I don't have good enough data. My experimental procedure was wrong. I've got to go back and do X, Y, Z. And then you share your results with others. So if you came up with what you consider to be a valid response, then you go back and repeat it. You share it with others, hopefully with some kind of a peer review. Peer review now is a whole different topic that I don't particularly want to get into. But this is how the scientific method works, okay? And if you're a professor or graduate student or a researcher and you've been working on this problem for years and years and years, the final thing is publishing your results. So that's the end right there. That's where you share with other people. In their version, this is so interesting, they have a table that they put up. This says textbook science versus science in practice. So they oversimplify the procedures that I just outlined for you to discredit them. They say that scientific investigations follow a codified step-by-step method. That is completely incorrect. Anybody who's studying geology is not going to have the same step-by-step method as somebody who's doing some kind of a virology study, for example, or a chemistry study, or physics. Like it's you've got the idea right, but it's not codified. Science works in isolation. No, it does not. Scientists collaborate with each other all the time. So, again, that's a completely incorrect statement. And anybody that's been in a classroom, whether it's a college level or a high school classroom, understands you're not working by yourself when you're doing an experiment. You've always got lab partners with you, always. Scientists use experiments to gather evidence. This is true. But as I said, sometimes you can't do an experiment per se. Sometimes you have to go out in the field to gather your evidence. So they purposely simplify it to discredit it. Scientific studies reach a firm conclusion. Now, this is the irony of this whole thing, is that the emphasis on consensus is throughout this entire how science works section, okay? The whole thing is about consensus science, and yet they discredit the scientific method because it says that studies reach a firm conclusion. So clearly it does not reach a firm conclusion. You agree with it or you don't, and there are a lot of studies that had consensus for, sometimes thousands of years. It took them a long time to get rid of the consensus. So, and then they put in a flowchart, which really is a very good representation of the scientific method, and they claim it's their new method of investigating, which is so much superior over the scientific method. It's like that's what you put in your flowchart. But the big thing here is their lack of emphasis on rigorous testing. They don't point out the fact that all three of these things can be disproved or falsified. And they insist that models are scientific knowledge when they're anything but. So those are all of the problems that I have with their version of the scientific method compared to what the traditional scientific method actually says.
You point out that a true prediction is about what will happen in the future, yet the manual seems comfortable with models that keep failing their own tests. Why does this distinction matter so much, especially in climate litigation that comes before judges?
Part of the problem with their models is that they really can't disprove or prove them because usually the predictions are decades in the future, right? So you can only predict something if you've got short-term response to your prediction, and they don't ever have that at all with the climate models. So that's a big problem right there. But they say in their document that a prediction is a logical consequence of a hypothesis, not necessarily what will happen in the future. But by my definition, and I would be willing to bet probably everybody else's definition of prediction is what will happen in the future. So this definition is completely confusing to me, how a prediction is not necessarily what will happen in the future. And it also takes away the fact that hypotheses need to be testable, right? And then they'll say that, this is a quote, the fact that there is a room for improvement in the process of science does not necessitate the distrust of hypotheses that have gained widespread acceptance in the scientific community and about which consensus has been achieved verbatim from their document. Okay? So doesn't necessitate the distrust of hypotheses that have gained wide acceptance. Excuse me? Like if you are a real honest and critical scientist, you're skeptical of just about everything. And the fact that somebody tells you, oh, this is the way it is, you should agree because 99% of scientists think that way, is that, well, there's a lot of other things that 99% of the scientists agreed with, and they were all wrong. So history backs up the statement that you should always be questioning. And if you find observations that don't support your hypothesis, that's the number one clue that you need to go back and revisit your hypothesis, because it's very possible that your observation is going to disprove it. And then they also say later, here's their contradiction. For a hypothesis to be testable, it must by itself or in conjunction with other hypotheses generate specific predictions. Okay, so we just read where a hypothesis doesn't necessarily predict, but in this statement, a hypothesis does predict. So which is it? Like, if you're a judge, you've got to be reading over this thing and thinking, what? What is it? What am I supposed to believe? Okay? And then they go through and make the following statement. It should generate specific predictions, which they define as a set of observations that one could expect to make if the hypothesis were true. I docked my students points every time they said the hypothesis is true. The hypothesis is only supported. So right there, it looks like we have somebody who really doesn't understand science writing this whole section. It's another huge red flag. And then in the context of testing hypotheses, the term prediction refers to a logical consequence of a hypothesis, not necessarily what will happen in the future. It's like there's so much mumbo jumbo in here, and it's constantly contradicting themselves. So this is a problem, and it's not just with predictions; it's with a whole bunch of other stuff too. But that seemed to be the most obvious contradiction, because you read it and they're going back and forth and back and forth. So that's a big problem for me.
When reading your article, I loved the historical examples you included. They really drive the point home that consensus is not the same as proof. You mentioned several overturned theories that were once considered settled science. Are there any particular historical cases that you think judges especially need to keep in mind when they're hearing climate or environmental cases?
Well, a lot of these historical ones were never really based on models, but they were based on concepts that had been accepted for so long that when evidence was presented that disproved them, people didn't want to agree with it because this wasn't the consensus. This is what we're seeing right now. So what are some great examples of this? Almost everybody is familiar with the concept of geocentrism, which basically means the Earth is the center of everything, the solar system, the universe, the whole 9 yards. This actually was first presented, or the idea was first presented by Ptolemy in 200 AD, okay? And it took about 1900 years ago. It took an additional 1400 years before that consensus was finally overturned. What overturned it? Well, we had evidence that was presented, calculations presented by Copernicus, and then visual evidence that was presented through the telescopes of Galileo, which completely disproved it. And again, even then, the consensus overwhelmed the contradictory facts. It took another few hundred years for it actually to be accepted. So consensus dies really hard, whether or not it's accurate. Eugenics is a very much a black eye, but it's not only a black eye on the history of the country, it's a black eye on the history of the world, which basically says that you can pick desirable characteristics from people in order to breed a superior race. That's it. It was first coined in the late 1800s by a British explorer, somebody who was adopting Darwin's theory of evolution and applied it to human genetics. Scientist was named Francis Galton. So it was really studied in earnest in the early 1900s, so like 20 years later. It became incredibly popular in the 1930s, where there were classes on it in public schools, in colleges. It was supported by a Nobel Prize-winning geneticist, a U.S. president, and a Supreme Court justice. It took almost 60 years before eugenics was abandoned. And the reason it was abandoned was because it was embraced by Adolf Hitler. So whatever it takes, right? And then the last example I'm going to give you, again, we'll go back to my geology background, is the theory of plate tectonics. So it started off as a hypothesis that was promoted or presented by a scientist by the name of Alfred Wegener, who in the early 1900s proposed continental drift. So he looked at a map of the continents, realized that they fit together like a puzzle, and his hypothesis was that they had formed one giant continent, which he named Pangaea, and over time they had separated out. This was not supported. The consensus at the time was that the Earth itself was shrinking, that mountains would form, that there were all kinds of processes going on inside the Earth. I remember asking my father, how do mountains form? And his explanation, which is what he had been taught in school, was that the Earth is shrinking, and as it shrinks, it wrinkles like the skin of an orange. This was the hypothesis, or this was the consensus. It took 60 years for them to overturn that. And it was in the 1960s when finally scientists who thought, yeah, this guy's got something going on, and looked for all kinds of other pieces of evidence before it was finally accepted and the consensus was overturned. Okay? So the judges need to understand that there has been significant evidence to disprove the hypothesis that carbon dioxide drives changes in temperature and changes in the climate. And those scientists have been dismissed by consensus. They're accused of being denialists. And all of these examples I've given you, the consensus was wrong. There was a paradigm shift, and that paradigm shift finally affected the introduction and acceptance of rigorous scientific experimentation and scrutiny. But today it's politics that drive climate science and the actual scientific method. So if you use the scientific method and you could come up with all ways to refute that carbon dioxide is the driver, then the scientific method is the bad guy. And the models and the predictions for 20, 30, 40 years in the future are what you should be listening to. So that's what judges need to keep in mind.
You make a very strong case in your article in saying that Judge Robin Rosenberg, who correctly removed the biased climate chapter, should now take the same steps with this How Science Works chapter. What would an improved version of this manual look like, and why is getting this right so urgent for the American public?
Well, they took out a perfectly good description of how science works and threw it out and rewrote a bunch of garbage to replace it. So think of a remake of a Hollywood movie where the original movie was really good and the remake was really awful, and that's kind of what you got going on here. So in the 2011 manual, they had a section called How Science Works, and it was written by a PhD professor emeritus of physics named David Goodstein, who was out of Caltech, and he concentrated on the actual scientific method. So what he did was he defined what the scientific method was. He took those same words that I had given to you before, the hypothesis, theory, law, explained what they were, explained how a scientific law is different from a law that you would have passed in, the judiciary, not in the judiciary, I'm sorry, by the legislature. And he included the concepts of falsification, paradigm shifts, and he also showed that he repeated, apparently there was a case in 1993 called the Daubert decision that talks about what should be accepted as scientific evidence. And according to the Daubert decision, maybe it's Daubert, I'm sorry, I don't know. These methods should be judged. All the methods that are used when they're presenting their data should be judged by the following 4 criteria. This is written in the original How Science Works document. The first one was that theoretical underpinnings of the methods must yield testable predictions by which the theory could be falsified. You can't do that with a climate model. 2, the method should be preferably published in a peer-reviewed journal. That today, with all the junk science going out, doesn't seem to be a problem. There should be a known rate of error that can be used in evaluating the results. In other words, what is your % confidence of this number? The best example I could give is whenever you're listening to polling, when they give it, on the news media, wherever, they'll usually say plus or minus 5 points or plus or minus 2 points. That's an error. In other words, you could take your actual value and add to or subtract to, and you would still be in this range where you would find your actual answer. But climate models can't include that, so they're not important. And then the methods should be generally accepted within the relevant scientific community. So the court itself defined scientific methodology as being derived from the scientific method. So the emphasis here is all on methodology. How did you get these results? You've got to demonstrate to me that you have good evidence to support your results, okay? And that they should be able to be falsified. What did you do to show that they were falsified? So there was really nothing wrong with the 2011 How Science Works. It was concise, it was clear, it was well organized, it was to the point, and it was an honest reflection of science, whereas the new one is like none of the above.
This concludes part 1 of my interview with Dr. Sharon Camp. We hope you'll join us next week for part 2.
Thank you for joining us on Climate Debrief. Executive producer is Angela Wheeler. Producers, Ethan Audie and Scott Wheeler. You can find more episodes of Climate Debrief at CO₂Coalition.org.